Good morning here in Pacific time zone, and welcome to our session today. We're still gathering together with attendees, so we'll give it a few more seconds and get this session started as we move forward. Okay, so let's get going with this. And first of all, I want to say, what a wonderful first session, and I know we're going to have a great second session as well. It's my pleasure to introduce the second session, and the title is pretty interesting: How Big Astronomy is Using Prevention Through Design to Succeed. And so, again, my name is Ed Gibson. I'm co-chair of this workshop, and I would like to introduce the moderator for today's session. The moderator is Mark Grushka. Mark is principal consultant, owner of MJ Grushka Consulting in Tucson. He's been engaged in safety as a safety professional for a large number of years. He's on our steering committee, and he's been engaged in helping us with our prevention through design and safety initiative here at Fulton Schools of Engineering since 2012, so 10 years now. And so without any further, I'll pass it on to Mark to introduce our session, and hope you enjoy what you're hearing. Thank you.
Thank you, Ed. It is a real privilege to be able to invite members of what I call the Global Astronomy Brain Trust to share their experience on how prevention through design has been integrated into a world-class telescope project being built in Chile right now. So Victor L. Krabbendam is the Vera C. Rubin Telescope Project Manager, and Chuck Gessner is the former Vera C. Rubin Head of Safety for the same project. So I think you will be very, very impressed with both the technology, but also the processes that were used to fully integrate prevention through design, and consistent with our theme for the overall workshop, the how. How was it actually being done? So without further ado, please roll the tape, sir.
Hi, my name is Victor Krabbendam. I'm a mechanical engineer by degree, and I spent my early career working on large optical systems for the government. I moved on to ground-based astronomy, having been part of the full development of two ground-based projects, the Javier Telescope in Texas and the SOAR Telescope in Chile. And I'm now the project manager responsible for the construction and development of the Vera C. Rubin Observatory.
And hi, I'm Chuck Gessner. I'm a mining engineer that started my career in mine design and project management. At the mining and smelting company, I was promoted to the director of safety and loss control and ran a large department of 45 safety and health professionals, serving about 6,000 employees. After that, I also moved to ground-based astronomy, mainly servicing the safety operations of telescopes. I am the former head of safety for the Vera C. Rubin Observatory project. An interesting topic that Victor and I often discuss is that we are both engineers, but when we were in school, there was hardly a word about safety and nothing about management or systems engineering. And yet we found ourselves steeped in safety design considerations, in management, and in safety management. So let's take a moment to review the Rubin project and highlight some of the features that drive the need for a strong safety culture. A focus on designing for safety from the start, and a robust tooling to support the goal of loss prevention.
We'll start by defining what we call the project, and by that we refer to the full development of the Vera C. Rubin Observatory, and we were previously called the Large Synoptic Survey Telescope. We started just after a compelling question and an idea began to inspire a community of scientists to think about a new observatory. A new system that, in fact, could address many compelling questions in astrophysics and astronomy. Our mission statement is provided here, but I leave that for you to read later. We began to trade off what was possible, what was desired, dreaming up a system and agreeing on requirements for capability and performance. Basically, we started with a blank mountaintop or blank slate and specified a complete system. We are well on our way to delivering this system, the RubinObservatory. This system includes a massive 8-meter class telescope, support facility on a remote mountaintop, the largest camera ever made for astronomy, weighing in at 3 tons, carrying 5 different filters and having a huge front entrance lens, and featuring a 3.2 gigapixel focal plane at the heart. Our system also includes a data management system that can take the captured image data from our remote mountaintop in Chile and move it to a data facility where it will be processed, archived, and we can serve those images, alerts, and data projects to scientists ready to harvest the database for their specific pursuits. Finally, the project also includes the development of an education public outreach system specifically tailored to engage with the global community and share the opportunity for exploration with the public. You might be thinking we have telescopes already and even bigger ones planned, and we have some in space that take exquisite data unobstructed by the annoying Earth's atmosphere. But the fact is that ground-based assets are still very viable and far-reaching, and the RubinObservatory is a world unique in its power and capability. Designed to take 15-second images of 3.5 degrees of the sky at a time, covering the entire visible sky every few nights, consistently in 6 optical bands, every night for 10 years. The system will alert on anything that changes on minute timescales through image differencing, and will use the 5 million images to produce annual catalogs and a massive 200 petabyte public astronomical database. So let's look at a few aspects that are key in this project that emphasize a need for formal tooling to support the safe development of the system. First, it's really about the timescales. The project spent from roughly 2004 to 2014 perfecting the science case and associated designs to establish the project technical, budget, and schedule details. At every formal review milestone, it was paramount to convey a clear handle on the technical scope, requirements, the programmatic risks, the hazards, and what we had in a plan to execute the project with the highest standard of safety. In 2014, we were authorized to proceed, and we are now well on our way to completing the $750 million project by 2024. The long duration of the gestation period, the ongoing drawn-out period of designs in complex, busy, and yet long construction fabrication period, and then 10 years of relentless automated operation drove us toward formal systems engineering and safety management tooling strategies. This slide, of course, is only the current period without the first 14 years and the next 10 as an example. Now let's take a real quick look at some of the technical and safety challenges of the project, and this is just a few. One thing that comes up often is what kind of an optical design do we have? And so here's just a quick animation to show you how light is captured from the sky, going through 3 reflective surfaces and into the camera. The primary and tertiary are fabricated into the same monster piece of glass, shown here at the bottom and shown here again in fabrication. We had to design it for safe operation on the telescope, but we also are responsible for getting it safely from here in Arizona, where it was made, to the mountain in Chile. Many design features are required to handle all of these aspects. The main telescope for the system is a 300-ton telescope mount. This is both the metering structure for the optics and the camera, but also the gimbal responsible for moving the position from position to position on the sky relentlessly. It is massive, fast, and has the capability to cause serious harm in regular operation, in maintenance, and especially now while we are getting the system working. The 30,000 square foot building to support the telescope operation, construction, and maintenance on the remote mountaintop is ripe with safety issues and hazards that must be identified early and mitigated early, or there will be limited options later in development and operation. The dome is not just a roof, but a 600-ton machine that rotates, has the main shutter, a moving baffle system to protect unwanted light from entering the shutter opening, has articulating vents for natural air flushing, internal cranes and passageways, ladders, platforms, and a large screen that plays a key role in the constant calibration of the camera and optical system. I can go on about how robust systems engineering and the safety strategies Chuck will discuss in a moment are key to the success of the project. But let me just point out that projects do not always go according to plan, and all these systems are key to the success of those situations as well. Finally, the Rubin construction is a complicated enterprise involving several hundred people on the project and several hundred working for contractors that all work together toward a common goal with the safety of personnel and equipment at the forefront of their activity.
So thanks, Victor. So we're going to talk a little bit about safety this point forward. We planned how we would manage safety in the days of the preliminary design that Victor talked about. And one of the first developments was the hazard analysis process. Other control measures, but are not limited to, but these are the major ones. The safety group is part of the senior management team. Anyone can stop work if there's a safety concern. Management sets the example for the safety performance. Contractors and collaborators are expected to have some safety systems, have the same safety systems of control. And then we also utilize third-party reviews to help us improve our safety performance. The safety policy recognizes and accepts different safety cultures within the project team. And it also emphasizes that the project has a minimum expectation for all those that work on the project. The Safety and Health and Environmental Plan is a complicated document, but it's also a compliance document that establishes the minimum expectations for employees, contractors, and collaborators on the construction site. It defines the best practices for things like lockout, tagout, confined space entry, other OSHA requirements, and world-class safety standards. This is a complicated project with hazards that needed to be identified and addressed. As a basis of identifying hazards, we used the MIL Standard 882 as our guide. In the early years, we convened our engineers from all trades and reviewed preliminary drawings to identify hazards based on our experience of designing and operating telescopes. As an engineer and a safety professional, I like the hazard analysis process because it allows engineers and designers to get their hands around safety during the design process. So these are the details about how we are managing the hazard analysis process. It's an iterative process and will continue and be reassessed through the project and on into Rubin operations. When subsystems interface, we collaborate with the subsystems engineers to identify additional hazards. We require this process with all of our contractors, and we expect them to contribute their experience to the hazard analysis process. So after the hazard is identified, we then determine the probability and severity of the hazard. From these two determinations, we can transfer these two assessments to the risk assessment matrix, and finally determine the risk level of the hazard. At this point in time, we've identified 218 hazards. The interesting thing to me is that 63% of the hazards that can be mitigated or minimized can be minimized by engineering design. Once the hazard has been addressed by the mitigation, or at least minimized, systems engineering identifies the proof of control. We call them artifacts. Could be photos, design drawings, a test, and/or a procedure. The artifacts are then put into a repository for future proof of verification, And finally, a safety professional reevaluates the risk level of the mitigation and presents it to the project manager for acceptance. Any hazards that have residual risk during the construction project will be turned over to operations management after completion of the project. It's important for the operators to know how to control that particular hazard. This slide depicts some of the high-level safety systems of control for the project. We thought about how we would improve safety and make the design of the observatory as safe as possible for the people during construction and on into operations and maintenance. Prevention by design requires effort and pre-planning way before breaking ground for any project. So this is how the project has done to date. Although any accident or injury is one too many, we investigate every accident and put into place control measures that reduce the risk of having a similar accident. As you can see, Rubin's safety performance is better than the U.S. national average. There is so much more that we are doing in safety compliance in the project, but we do have very limited time in this presentation. We would be glad to answer any questions that you may have in the breakout sessions.